Hi, and welcome to video 4 for section 1.2 for Math 126. This is the fourth of 4 videos. And in this video, we're going to be dealing with a pretty important topic. We're dealing with radicals. So roots of a number, square roots, third root, etc. I can't stress how important this section is going to be. I teach Math 127 as well. And in Math 127, it's a trig-based course essentially. We use a lot of radicals. So when we're talking about radian measures, we're going to be dealing with square roots a lot. So you need to be comfortable, if you're someone that has to go on and take 127 and then even 181, maybe comfortable is not the right word, but you need to be confident at least in terms of working with radicals. And so this video, if you need to watch it a couple times, if you need to do some more practice, let me know, and I can give you guys supplemental worksheet, things like that, because it's important that you understand these concepts. So by definition, if n is any positive integer, then the nth root of a is defined as we have this notation. So the nth root, you guys probably call it the square root symbol, but it's really just a root symbol. So the number in front here is what root we're talking about. If we're talking about squared roots, we're not going to write in a 2. But anything other than that, third root, fourth root, fifth root, etc., we would write that number in. So the nth root of a is equal to some number b. And what this means is, if I took this number b and raised it to the nth power, it would give me the value of a back. If n is even, then a has to be greater than or equal to 0, and b would have to be greater than or equal to 0. So some examples here. What if I have this? So as I told you, if there's nothing written in front here, it's like an invisible 2. So I know in algebra a lot, we always have this invisible 1. So like if x equals 3, that means 1x equals 3. We don't write the 1. When we're dealing with roots, if the number's not here, then it's basically the square root. So we want to know what number squared would give us 16. So that is, of course, what? 4. Because 4 squared would give me 16. Cube root of 8. So what number to the third power, so that means what number multiplied by itself 3 times would give me the number 8. So if you remember earlier on in section 1.2 here, we talked about exponents. And so this is essentially reversing the process. So I want to know some number, let's put it in parentheses, some number to the third power has to give me 8. That's what this thing means. Cube root of 8 means some number to the third power is 8, and that number would be what? 2. So that would be our answer here. So because 2 to the third power gives me 8, so therefore the cube root of 8 is equal to 2. How about the cube root of negative 8? So when we have a negative number under the root symbol, at least for now, later on in the semester we'll deal with sort of other options we have, but for now, for section 1.2, if I have a negative underneath this root symbol or the radical symbol, so let me give you guys a couple definitions here. So the root is n, the radicand is the number underneath, and then the radical symbol is that root symbol there. So what number, if this is negative, the root at this point has to be an odd number. Again, like I said, later on in the semester we'll deal with other possibilities. But for now, negative underneath, that's fine. So what number multiplied by itself 3 times would give me negative 8? Well, we know from example number 2, 2 to the third power gives me positive 8. And so similarly, if I do negative 2 to the third power, that gives me negative 8. So negative 2 times negative 2 times negative 2. Negative 2 times negative 2 is positive 4. Positive 4 times negative 2 is negative 8. And then fourth example, how about the square root of negative 16? So let's think about what this is asking. Square root means that some number multiplied by itself is going to give me negative 16. That's not possible, right? Because if I have 2 positive numbers multiplied by each other, it'll give me a positive number. If I have 2 negative numbers, the same number multiplied by itself, negative, 8 times negative 8 gives me a positive 64. So no matter what number I choose, I'm not going to get a negative back. So for now, for this section, if you're doing the homework, your answer is going to be not a real number. Again, what is chapter 1 all about? It's about real numbers. So at this point, if we have something like this, square root of a negative number, our answer is simply going to be not a real number. All right, so how about the properties of these nth roots? And again, this you're going to want on your cheat sheet, highlighted somewhere maybe in your notes for quick reference. And as I said, you're going to be using these properties even in the Math 127 and 128. So, I give you guys a cheat sheet. If you want to call it like a quick reference sheet while you're doing homework and so forth, that's fine. But have this somewhere easily accessible so that if you're doing these kind of problems, if you don't remember it off the top of the head, you can just go back and check real quick. So if I have the nth root of 2 numbers multiplied underneath, a times b, I can separate these, nth root of a times the nth root of b. So if I have a radical, some number underneath, I can split the number up, I can factor it if I want, and then separate it using that nth root to simplify this number if I need to. If I have a fraction underneath, so the nth root of a over b, again, I can split it up as the nth root of a over the nth root of b. Third property, if I have the mth root of the nth root of a, so I have 2 different roots going on here, this is the same as if I multiply the roots m times n, and that becomes the new root for my value a. So again, it's kind of reversing the process. If you remember the power rule with the exponents, if we had a to the m to the nth, we could just multiply the exponents. Same thing here. If I have a double root, I can just multiply the roots. Number 4, if I have the nth root of a to the nth power, this is just equal to a if n is odd. So let's do one of these guys. And it's equal to the absolute value of a if n is even. So for example, I had the third root, let's do this here. So i.e., if I have the third root of -2 to the third. Well, basically the 3's almost cancel each other out, so I just get -2. Whatever that value was, an exponent on the inside, that's my answer. If I have the fourth root of -2 to the fourth. So you remember over here I was telling you what, if we have a negative underneath the radical symbol, if it's an even one, it's not a real number. But here we have to deal with this property, because what happens? If I did -2 to the fourth to begin with, that would be 4 negatives multiplied by each other, which ends up with a positive number, and now I could take the fourth root. So this is just the absolute value of whatever a is, so in this case -2, which would be +2. And then lastly, if I have a to the m over n, so this is the one you're going to be using a lot. This allows us to convert from radicals to exponents or exponents to radicals. So this is equal to whatever is in the bottom of this fraction is my root. So that's going to go in front of the root radical sign. And then a with the exponent of whatever the numerator was. So the key is whatever, if you have some number with a fractional exponent, the denominator of that fraction would be the root. Or another way we could write it, if it makes it easier on our math, would be the nth root of a, all of this to the m power. So for example, if I have, how about 4 to the 2/3 power? If I want to write this as a radical, the denominator is 3, so it's going to be the third root of 4 to the second power. So 4 to the 2/3 power is really the same thing as saying the cube root of 4 squared, or cube root of 16 if you wanted to. So with all of these, it had to do with basically simplifying our life here. There was no addition, subtraction, anything like that. So let me give you this note, and this is, again, super critical because I see this mistake all the time where people don't follow this rule. That's why I'm writing it in red. If you got a red pen, write it in red so that you don't make this mistake. When adding or subtracting radicals, the root and radicand must be the same. So if I have the square, so let's do another IE, square root of 3 plus square root of 2. This is not the square root of 5. I can't just say, oh, they're both square roots, so I add the numbers underneath. No, 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 do not do that. The roots are the same, square root, but the radicands are different. The only time you can combine these things, think of these as like x's and y's. If this was x plus y, well, you can't do x plus y is just xy. That's not the way it works. But what I could do is if I have like 2 square root of 3 plus 4 square root of 3. So if this is like an x, 2x plus 4x is 6x. That I can do. The roots are the same, the radicands are the same. So I have 2 square roots of 3 and 4 square roots of 3. So what I have really is 6 square roots of 3. So that's the only way we could add or subtract if there was a minus sign there. It's the only way that we can do it. So What if I have this? The square root of 32 plus the square root of 200. The roots are the same. They're both square roots, but the radicands are different. So what's my answer? Do I just say, that's it, I can't do anything? No, of course not. It's never that easy, right? But I can use some of these properties here to try to simplify it to see, can I get it to have the same root and the same radicand? So square root of 32, let's work with that one first. I can break up 32 by property 1 as what? 16 times 2. So 32 is 16 times 2, so square root of 32 is the same as the square root of 16 times 2. Now using property 1, I can split these. Square root of 16 times the square root of 2. So why did I choose 16? I also have what, like 8 and 4? I could have done that, I guess. I'll just have to do more work. But because I have square root, I want to try to pick the biggest square number, so 4, 9, 16, 25, 36, etc., so that later when I have to simplify, then I could actually take a square root. Because if I did, let's say I have 18, square root of 18. Well, for me to break this up as square root of 6 times 3, that doesn't do me any good because I have square root of 6 and square root of 3. Those don't really simplify into a nice easy number, so it doesn't help me. But I could do 9 times 2 because what? Then I have square root of 9 and square root of 2. Square root of 9 is 3, so this just becomes 3 square root of 2. So because I'm dealing with a square root, I want to try to pick a squared number so it'll simplify later. And that's what I have at this point, right? Square root of 16 is 4. So square root of 32 I can really rewrite as 4 root 2. And we'll shorten that up. Instead of saying 4 times the square root of 2, we just say 4 root 2. That's what this means here. So how about 200? So why don't you go ahead and try it. Hit pause real quick. See if you can break down 200 into a way that we can simplify using some of these properties and get something else that has a square root of 2, so then we can add them as we did up here in the previous example. All right, hopefully you got it. So 200 we can rewrite as what? Well, I want a perfect square if possible, so that's what? That's 100 times 2. So if I break this apart, square root of 100, square root of 2, square root of 100 is 10. So the square root of 200 is really 10 root 2. So now because they both have square root of 2, I can add them together. 4 plus 10 is 14 times the square root of 2. So that would be my answer. Square root of 32 plus the square root of 200 is just 14 root 2. All right, I'm going to leave the properties here. I'll erase this, so if you need to still write or catch up or follow through, go ahead and hit pause. Otherwise, I'm going to erase it to do these last couple examples so that we have these properties to refer back to here. All right. So the last thing we're going to do here is simplify radicals as rational exponents. So again, I mentioned how important being able to convert back and forth from radicals to exponents and so forth. This is going to show up on your exams in class. Probably going to show up on the final. So what we're going to be doing here, we'll do a couple of them, but if you need more help, you need more examples, let me know. I can give those to you. So let's say for our first example, we want to simplify 2 times the square root of x times 3 times the cube root of x. So because we have a square root of x and a cube root of x, we can't do property 1, right? Because we have to have the same roots. If it was cube root of x and cube root of x, then we could combine it because it's the same root. But because it's not the same root, our only real option then is to convert these to exponents. So we have 2. So if I'm converting this to an exponent, it means that it's going to be, because it's a root, going to have some fractional exponent. And what did I say over here? Whatever the root is, that's the denominator of this fraction. Well, this is what? This is square root. So that means what? A 2 goes in the denominator. In my m, the number in the top of the numerator, or in the numerator of the fraction rather, is whatever power is attached to the number inside. So this is like x to the first power. So it's really 2x to the 1/2 power is the same as saying 2 times the square root of x. Yeah, I'll put this in parentheses. And then what do we have here? 3. Well, the same idea. It's x. It's going to have a fractional exponent. The root is 3, so that's what goes in the denominator now. And again, it's still like to the first power on the inside. So it's 3x to the 1/3. So this is multiplication. So I can change the order, right? Remember, multiplication is commutative. It doesn't matter what order I do it. As long as it's multiplication. If this was addition, I couldn't do that. So I'm going to rearrange this. So this is what? 2 times 3 times x to the 1/2 times x to the 1/3. So 2 times 3 is what? This is 6. Now I have x to the 1/2 times x to the 3rd. So remember back to our exponent rules. If I have the same base and I'm multiplying together, what do I do with the exponents? I add them. So this part here is like x to the 1/2 plus 1/3. So I need to simplify this. So now going back to our fraction video, so you can see how this is all building on each other. If I have different denominators, what was the process? Well, the final denominator will just be these guys multiplied together. So 2 times 3 is 6. And then remember, I'm crossing this way and adding. So 3 plus 2. So if I simplify this, this is 6x. 3 plus 2 is 5. 6 in the denominator. So my original one, 2 times the square root of x times 3 to the cube root of x, is the same as 6 times x to the 5/6. All right, go ahead and hit pause if you need to catch up, follow through, rehash back. We'll do another example here. So we have the square root of x times the square root of x. So, I know it's early, you just learned how to do this, you only just saw one example, but go ahead and try this one. I'll give you the hint, work from the inside out. So, change the inside one, simplify it, change the outside one, simplify it. So like I said, go ahead and hit pause, give it a try. If you get stuck, fine, then hit play again. If you're not even sure where to start, then just hang out for a second. Otherwise, give it a go, come on back and see how you did. All right, hopefully you're able to tackle this one. If not, like I said, it's still early, so wouldn't really expect you to get it necessarily right off the bat. If you did, that's great. So we're going to work from the inside out. So we have square root of x times, well, the square root of x is what? In the last example, we saw that's the same as x to the 1/2 power. So it's x, I'm going to have a fraction, the root is 2, that goes in the denominator. There's like a 1 here, so that's 1/2. Now combine these guys. So I have x, because they have the same base, so this is like x to the first power, but because this has a denominator, I'm going to write it as 2/2. So again, there was nothing here to start with, but because they have the same base, I add the exponents. And so what was my exponent here? It's 1, but 1 is the same as what? 2/2. And I do 2/2, that way I have the same denominator. So here I have what? 2, the denominator is 2, so that stays my denominator, and then the top is 2 plus 1, which is 3. So x times x to the 1/2 is x to the 3/2. Now, I can rewrite this again using my exponent notation. So this is what? This is x to the 3/2 to what power? Well, the same property holds. It's going to have a fractional exponent. The root is 2. And if I think of this whole thing as this guy to the first power, so that's this format here, then that means what? That means there's another 1 here. So it's x to the 3/2 to the 1/2 power. Now I use my exponent laws, and I get what? X to the 3/2 times 1/2. So when I have a base to a power, I multiply the exponents. So when I'm multiplying, that's the simplest of my fractional math. I just multiply everything across. So 3 times 1 is 3. 2 times 2 is 4. So x to the 3/4 power. So the square root of x times the square root of x is really just x to the 3/4 power. So again, maybe the tricky part there was like right in this area, converting this one into a half. But anytime you have a square root, that's always going to be the 1/2 power. Or if you have the cube root, that's always going to be the 1/3 power. So you can think of it two ways. Either this guy, x to the 3/2 to the first power, and that's how we get a half. Or you could think of it as x to the 3/2, the square root, all raised to the first power. And then again, that's how we get from this line down to here with x to the 3/2 to the 1/2 power. And as I said, then we're going to use our exponent rules. So that's it. Hopefully you guys were able to get this. If it is, I mean, that's great. You know, before you started this video, you probably wouldn't have been able to simplify this. Now hopefully you have some idea what you need to do. As I said, practice the examples in the book. We can do more in class if you need to so that you feel comfortable with it. That's the end of video 4. That wraps up section 1.2. Come on back and we'll tackle section 1.3.